So, good afternoon, folks. I'm Stefan from Excellent, and Robert, my colleague, and we will tell you today a story about our journey migrating our software from supporting Cumulus as a NOS to SONiC as an additional supported NOS. We are from Excellent Technologies and located in Munich, Germany, and we are the founder and main contributor of an open source project called MetalStack.io, which is an implementation of bare metal as a service cloud implementation. And this was started back in end of 2018, beginning of 2019 for a financial customer to provide Kubernetes as a service. We will talk about that later. And we started with Cumulus, as a lot of us did back then, because SONiC was for us at that time totally new. It was founded, I guess, at that time. And we started with Cumulus, and we're pretty happy with it within the last 5 years and in production since then. But Cumulus come to an end, and we have to add support for SONiC as an operating system on the switches. And today I give you an inside view how we did this, what we are actually doing with MetalStack, and what our hassles and outcomes. So MetalStack, just to give you an idea what we are actually doing, is a set of microservices. So we are mostly software developers, not network engineers. A set of microservices we implemented. It's open source, and it's a metal as a service. So think of and we provide an API for your data center where you can order machines and networks in an elastic way. So it feels like virtual machines, but you actually get physical machines in the same speed as you get virtual machines. So to explain it a bit in a picture, imagine you have multiple data centers with multiple racks and hardware deployed there. So physical servers from with 1 or 2 socket machines, and all of them are connected to the switches in a cluster topology. And there is a central API running this blue box in the middle. And this blue box in the middle knows exactly how many machines and network switches you have in all of your data centers. And you can talk to that API, please give me physical machine with the specs in that particular data center. With this operating system. And you can also say, give me an extra network for me alone. So tenant separation is done on worth basis. And this blue box will then check where is available machine with the given specification, and will create that machine. And after 2 minutes at most, the machine is ready to get used to. So it's up and running, booted into the Debian 12, located in the newly created network you ordered, and ready to be used. This is not the original use case we designed it for. The use case is to use that API from a higher level set of microservices which orchestrates Kubernetes clusters out of these physical machines, but this will be too much to be explained in this talk, because I guess you are not all Kubernetes experts here. We stay on the network part. And what this Metal API does, it orchestrates the network part and orchestrates also the installation of the operating system with the matching configuration on the network side as well. And this is all done in the mentioned 1 to 2 minutes. So it's quite fast. And you will ask, why do we orchestrate bare metal to generate Kubernetes? You can use virtual machines. It's already there. It's implemented. And why not using virtual machines? Why implement the automation of bare metal provisioning? Because this is quite a hard job. The reason for that is there are several reasons for that. The financial industry is quite sensitive for performance, for tenant separation, for mitigation of CVEs and in CPUs, for example. Also for effects of noisy neighbors. So imagine you have multiple virtual machines running on the same hypervisor, and one customer consumes a lot of I/O, for example, then all other customers running on the same hypervisor will be affected. There's also one big disadvantage of using virtualization for Kubernetes worker nodes is the growth of the stack. So Kubernetes itself is quite a big software stack, and Kubernetes just runs containers, and the need for virtualization to separate applications from each other is not there anymore. So if you strip out the hypervisor, you get a simpler stack. So your container is running on the physical machine with no additional software in between. That makes the software running more reliable, more faster, and it can leverage more of the provided I/O. We were talking about 100G networks or NVMe drives. With virtualization, this will not be able to consume at the very, very limit. Of course, there are downsides of using bare metal machines instead of virtual machines. You are affected by hardware failures. So if for example, a power supply fails in a hypervisor, you can evacuate all the virtual machines, replace the failed hardware, and then the virtual machines will see no downtime. This is not possible with physical machines. You also cannot over-provision your hardware, and you cannot live migrate, obviously. So physical machine is a physical machine. If the binary runs on that machine, it runs on that machine. But with Kubernetes, you can mitigate a lot of these downsides because Kubernetes itself has its schedulers, which restarts failed applications from one machine and restarts them, if possible, on another machine. Okay, we're using actually bare metal switches and bare metal servers, switches from EdgeCore, the famous 7726, started with Cumulus 3.7. And actually, right now, we have the enterprise SONiC from EdgeCore, and we always have a twofold cluster topology with spines and 2 leaves per rack. So every machine is connected with 2 uplinks to 2 different Tor or leaf switches in every rack. And the servers are vanilla, Supermicro, x86 machines, all of them with the same NIC from Intel actually, and we deploy Debian most of the time. For some reasons also Ubuntu, and we always use FRR routing for the machine size networking because we use routing to the host with BGP unnumbered. So this was a very important decision right from the beginning, which we will never go back. And how does actually the deployment on the switch works? If a machine gets created, we do not have some CI/CD. We have our own controller which runs on every switch. It's a container application running in a container on every switch, which is connected to our central API and consumes all changes which are required to every switch. So our central API has always the knowledge of all data centers and all machines, and in which network every machine needs to be connected, either in a VLAN for the PXE boot process or in a VRF which gets newly created for a new tenant. And once a machine is created, the small controller on every switch gets notified, okay, here a machine needs to be created. Please change the ports of this machine from the VLAN where it PXE booted actually to this VRF. And this controller then reconfigures the switch during the machine gets installed. So that's the reason why this deployment process takes only a few minutes, or only less than 2 minutes. We also create firewalls for every tenant in front of every worker node in the same way. So a firewall in our scenario is also a physical machine which connects the different VRFs, maybe the data center network or the internet network, to the tenant network, and regulates the traffic in between with firewall rules deployed on that physical machine. So, and in the Cumulus days, we created 2 configuration files with this small controller. It creates it's a network interfaces file because Cumulus is Debian, as SONiC as well, but the whole Cumulus switch configuration is done in 2 files, basically, the network interfaces and the FRR config for the BGP configuration. And after we have written these files, always the whole file with the whole configuration, so we do not do any incremental modifications. If reload and FRR reload was sufficient to apply the newly created configuration on the Cumulus switch, and then the switch port affected by the new machine changed its configuration. This was was our approach for Cumulus, and this is working fine on about 100 switches since 5 years. And we were thinking about doing the same approach at the beginning at SONiC as well. So we wrote a whole config.db JSON, which is the central configuration file of SONiC, and did a config reload. But this was a bad idea. And Robert will talk you why this was a bad idea.
Yes. We started with a migration from Cumulus to SONiC 2022, in early 2022. And of course, you can try to use config load, but config load will reset the whole switch state and all links go down, forwarding state is lost. So we need a solution that doesn't reset the state of a switch. So we try to use config reload, and config reload will load the config.db JSON into the running state and merge everything together. But the issue with that approach is you cannot remove entries. You cannot remove configuration with config reload. We try to set some entries to null. It works with some approaches, but not with everyone. So this was not a solution for us. And we also tried the config apply patch and config replace. This allow us to also remove stuff in the config.db and to modify and add new configuration into it. But because we are switching interfaces from a VLAN into a VRF and back again, depending on the state of the machines, it looks like what for SONiC the order of the request matters. So, and the config apply patch and config replace, we cannot force a specific order. It's not clear how he's doing the stuff. And in some circumstances, the org agent crash and the whole container as WSS goes down and the whole state of a switch is gone again. It's like a config load, so this doesn't work. And also we have to use unnumbered PGP, and we cannot configure the unnumbered PGP with a config DB JSON. We can configure numbered PGP with a config DB JSON, but not unnumbered. So we have to stick with the old approach what we have used with Cumulus to write a whole FRR configuration and load it into FR routing daemon. And yes, this was also a very nice finding what we in the first place doesn't understand completely, because in Cumulus every font panel gets its own unique MAC address. In SONiC every font panel gets the same MAC address. This was very surprising for us, because we need to identify the font panels of the switch from the node per LLDP. So we have to find a different solution, and also to reconfigure the hello timer on the switch per LLDP. And the last one, the FFR reload Python script, what is very convenient to put the new configuration in the FFR routing daemon, is not shipped in a community SONiC. It was decided by the community to not to do it. So how do we come to a solution? So in the end, we decided to modify our little controller to write directly in the Redis database, directly in the config.db database. We do it by checking the current state and calculate what is required to get to a desired state, and inject the required configuration in the correct sequence of orders. And we use the same approach from Cumulus, write a full FRR configuration and trigger the FFR reload Python script. For that, of course, we have to adjust, modify the BGP container to also include this nice Python script. And to get a workaround for what every font panels use the same MAC address, we figured out we also can use the port alias, because for us it's enough. We only have to identify the font panel. The MAC address it's only for the identification, and it's very nice. The LLTP package also includes the port alias. So, and with all of that, we create a first approach and tested and found some nasty bugs. Because it's not only the order of the inserts matters, it also matters the timing between the inserts. Because if we remove an interface from VLAN, we have to wait until this change is propagated to the whole SONiC switch. If we do not wait enough and try to put this interface in a worse, watch agent crash again. So this means we have to watch really the ASIC DB, the state DB, to figure out, is this interface still part of a VLAN after we trigger to remove it from a VLAN, and the other way around too, because if it's in a verve and it's still in a verve and I want to put it in a VLAN, everything crashed again and the whole switch is resetted. So, but with all these changes, we get a working proof of concept with a virtual switch image from the community, and was very interested to see how it's working with real hardware. The first issue was the community SONiC doesn't work on the Edge Core 7726, and we cannot figure out how to get a working solution. Of course, maybe one approach would be to create our own community SONiC, but we have not the manpower to do that. We only 3-4 people to maintain everything, and for us it's too much. So we looked around and tried the Edge Core Enterprise SONiC solution, and in the first place it doesn't work because layer 2 EVPN didn't work. There also exist different kinds of issues, what results in crashing Orch agent and also the FFR routing crashing. Because this stuff could only be found out because we are using a whole topology with real hardware, and it happens. So we created several bug reports and have to wait until it gets fixed. It was very hard for us to reproduce everything because we have no access to the source code of the Edge Core Enterprise SONiC. Of course, I have access to the community SONiC source code, but it's a lot different things from my side. And also we have no virtual image from the Edge Core Enterprise SONiC to test it. So, and after waiting a lot of time, the bugs get fixed, and also we can use some very nice features what are still not present in community SONiC. For example, you can configure the hello time of LLDP, or the FFR reload Python script is already shipped with the Edge Core SONiC. And for a different customer, we also looked into Enterprise SONiC by Volkman, and of course, you also have some issues with everything because it's also very different in some kinds to the community and the Edge Core SONiC. You can find all our implementations on GitHub. Everything is open source. Right now it's working in production. We have sometimes minor glitches. For example, if we want to use the next minor or the patch version from some Enterprise SONiC, some new features come into what are not backward compatible, like the Agent X protocol, what is enforced in the FFR routing. So it's still hard to maintain it because we still have no access to a virtual switch image for every distribution. But in the end, it's a lot faster comparing to Cumulus, or?
Yes. Thanks, Robert. As Robert already said, we are in production with SONiC switches since almost a year. And compared to Cumulus, we have way faster reconfiguration times. So it went down from several seconds to reconfigure the whole switch to sometimes some 100 milliseconds, which is great. Also, the CPU load on the switches is lower than on Cumulus. And of course, now we have an up-to-date open source still available, or hopefully more available NOS on our switches running than with Cumulus, because this is dead. But we have a really long wish list. Some of the topics were already pointed out by the first presenter. What we really would like to have is hardware support added by all the vendors in the enterprise distribution should be contributed back into upstream SONiC deadline. Not someone in 2030, but near time. We are software developer. We're coming from the Kubernetes world, and we really would like to have that SONiC has a unique configuration API for all aspects, which includes FR as well. We are dreaming of something like a manifest where you define the desired state, and some controller on the switch reconciles that to the actual state and watches on changes on these manifests, so-called. So it's a Kubernetes manifest is always watched by a controller, and what is written down there needs to be the next current state in hardware or in reality. And this would be, from my opinion, required for the next few years to have something like this in SONiC. Our small controller called Metalcore is something like this, but on a very small surface. So we only support our very small and very restricted set of features we need. We don't need MLAC, for example. We don't need a lot of the layer 2 stuff. Only verse, only BGP unnumbered. So the whole difference between the upstream open source SONiC distribution and the enterprise SONiC distributions is kind of what we actually see in the Linux distribution space. So Red Hat Enterprise Linux is something totally different than Debian, for example. We prefer Debian. We don't like Red Hat Enterprise Linux so much because Debian is a full open source, open Linux distribution, and we would really like to have the same ability to use the open source upstream SONiC distribution on our switches. Also, we develop locally on our laptops in a virtual environment where we spin up the whole topology we see in our database locally, and therefore we need a virtual switch image, which is not available for EdgeCore Enterprise SONiC, for example. It's available for the Broadcom, but same problem as I described above. There's a difference between behavior and availability. So that's all from our side for now. What we have is, based on that technology, also a cloud offering for managed Kubernetes on this bare metal offering in Germany, located in Munich, operated by us and developed by us. Metal Stack Cloud, if you use this voucher, you will get an €100 voucher and try yourself Kubernetes on bare metal in minutes. So it takes 5 minutes to get a new Kubernetes cluster. So thanks, guys, and enjoy.
Thank you. Any questions? Yes. Have you considered upgrading FRR during your journey?
It doesn't work. Doesn't work.
Meaning you try it and it doesn't work?
Also, we always update FRR on all of our machines.
So you didn't use the community version, basically?
Yeah. We use on the machines FRR from upstream 10 since...
Version 10. Okay.
But on the switches, it doesn't work. Okay. It's a fork, completely abandoned fork, which is used in SONiC.
Yeah, version 10 is forking off, but version 8 is still much more advanced than what the community has. So
yeah, it's also a hassle. It didn't point it out.
Thank you.